So if you all remember, yesterday I was supposed to get through this whole talk on system design and innovation, a garbage collection case study, but we didn't. So I'm going to go back and review just a little bit of material, and then move on from there. So one of the most popular and widely used collectors is called G1, and the name was Garbage First. So in the old space, it had some techniques to try to find where garbage was most likely to be and collect those regions. And it has a old space free list, and it has a copying nursery. And then it operates in a stop the world fashion, okay? So it has parallelism, as we showed in the little diagrams. We have parallel threads going, then we stop the world, and then we have parallel GC going, and then we restart the world. So there's much more to that than the G1 collector, but those are the high-level abstractions that I want you to be thinking about as we dive back into garbage collection. So what's going to happen now is concurrent collection. And what does that mean? That means instead of stopping the world and doing all your garbage identification and reclamation work in those pauses, we're going to do some of the work together while the application is running. Okay? So the most popular collector that does this is Shenandoah, but the first one to do it is C4, and ZGC is a variant, has some similarities with Shenandoah and was developed about the same time. So what's different now is instead of stopping the world for a long time, we stop the world for a much shorter time, and we do something called snapshot at the beginning, which says every write that happens while I'm doing this collection, I'm going to store it in another special write buffer, and I'm not going to let it bother me as I try to finish the trace of the whole heap. So when you stop the world and take a snapshot at the beginning, you incrementally find things that change, but you assume that everything that was live when you did that little bit pause is what the live set you're going to find in your trace, right? So you're not trying to find more garbage as it becomes garbage, because that makes the write and read barriers much more complicated, all right? But in order to do concurrent copying out of the nursery, or concurrent copying in the old space, which these collectors also do concurrent copying in the old space, that you have to do a read barrier. And though that had a lot of cost that wasn't really recognized until recently. All right, so let's show a little bit about GC pauses versus application latency. So the LU search benchmark is an enterprise search engine that, like Disney and other companies that have a lot of search on their websites, host. And it's been packaged up into a benchmark. And so the latency of each query is similar to, is a little slower than Google search, but not doing as many things. But it's a latency critical application. If you don't search fast enough on the Disney website, for example, then people don't come to Disney and abandon the website. Like, you need responsive search. So in this case, the pauses of Shenandoah are significantly smaller than the pauses for G1, which is to stop the world. But if we look at the latency of the requests and we plot them in their percentiles, so going from the 0th percentile to the 99th percentile to 100, then the tail latency and even the median latency starts to get significantly worse because of all that extra work that you're doing on the applications records. Does that? Yes? Ricardo, thank you.
How big of a problem is it, like, from a client standpoint, I guess, if
So that's a great question. So if you have a big database of things you're searching, the 99th percentile or even the 90th percentile can show up very frequently when you're gathering all the queries together. So if you've got 100 servers that you need to look at the different shards of your database on whatever you're serving, then one of those is likely to be long, and then all of them, then you can't give a result to your user. So the optimization is like you're trying to get the 99th percentile to be good, and that's why we're showing it. Good question. Thank you, Ricardo. And thank you for setting the example of saying your name. In the back.
Keith.
Keith?
Okay, so I want to ask, why is it that the latency is so much worse even though the interrupts are pretty much comparable? It's something to do with the write barriers having...
The write and read barriers.
Right.
Okay? And let me show you a slide I was going to skip, which is called the least upper bound analysis. And what that does is it says ignore all GC time, take all GC time out of it, and just measure the time overhead on the mutator, and say what the lower bound is of that, and normalize to that. And the lower bound in this case, 1, is the semi-space collector, because it has no read or write barriers. It's normalized to 1, and it has a great locality, and then you just ignore the GC time. And so then in a tight heap, all the collectors have overhead, and the LXR collector that I'm about to show you, even it goes up to a little over 20% in that very tightest heap, but you can get it down to under 10% on the mutator overhead. But G1, Stop the World, has simpler read and write barriers and no read barrier, and then these more concurrent collectors that get that pause time down, but they sacrifice too much on the read and write barriers inserted everywhere. Okay? And so now I'm going to talk to you about how to only have a write barrier. Okay? And then use reference counting to get immediacy and some other good properties to not copy during the mutator, which is concurrent copying is the enemy here because it requires a read barrier. Because when you move the object, you don't want the mutator to miss the move, right, and access the old version and read the old version when they should be reading the new version. So that's why it requires a read barrier. All right, so the LXR collector uses the IMIX heap because it gets you a bunch of good benefits, and then on top of that, it adds immediacy with reference counting in the pause. And it's mostly doing increments in the pause, but it also does some decrements in the pause, and I'll use the full word since I got called out on using inks and decks yesterday. And it avoids concurrent copying, but it still does avoid concurrent copying. So if you'll remember from yesterday, you would pick some target blocks to copy into and some source blocks to copy out of because those source blocks were fragmented. So you need to do that even more judiciously. So you're only copying a little bit, and how much can you copy? Well, you tune that based on what kind of pause times you want to see, and trying to get that pause time still to be short. All right? And then the low latency, you do reference counting frequently enough at a pretty good interval, either based on the allocation rate, which is essentially the best way to do it, or more sophisticated heuristics on when to keep that immediacy coming. Someone had a good question yesterday at dinner, which was about real-time garbage collection, and you have to, and profiling. So you might have a program that's allocating in big hunks, and then everything dies at once. And so the reference counter would find no garbage until that event happens. So there are you can drive this into corner cases where it won't work, and you could use other approaches to find that. So the snapshot at the beginning is critical to all these concurrent algorithms. So we're also using that right barrier, and then we needed to add a little bit more to that right barrier to do reference counting in the right barrier, as well as concurrent tracing. So if you're interested, that's in the 2022 PLDI paper that describes that right barrier. And then since reference counting is incomplete, what we do concurrently is trace the heap in order to find those dead cycles. So I'll show you a picture of how that works, because I think that this is the most intuitive way to me. And if it's too small to read in the front and you're in the back, you can turn around because it's also on the back slide. All right? So the little red stop the world pauses are longer than, for example, pauses in Shenandoah. And they do two kinds of work. So they perform the reference counting increments, and they perform some of the decrements, and they perform a fixed amount of copying that's budgeted so that you can keep the pause as a bounded time. All right? So it says I want to perform all the increments, because if I don't perform the increments, I can't reclaim anything, because I don't know if it's dead or not, because if you don't perform all the increments, a zero is meaningless, right? So you have to do that in the pause, and then in order to reclaim something in the pause, you need to do some of the decrements, but you don't need to do all of them, all right? And so if you run out of time on your decrements, you can put those into doing later, and so those are called lazy decrements. And how much memory you get back, this is more like a real-time collector, but it's not a real-time collector. How much memory you get back helps you tune those parameters and how small you can really make this pause, okay? And then you also give yourself a budget for how much you can copy in each pause, and if there's fragmentation or not that you want to get rid of. So you use both those criteria. Is the heap fragmented? No, it's not causing me any problems. Does it have some fragmentation? Yes, so I'm going to fix some of it on every single GC for a while until I'm in a better place. All right, so not in the pause is lazy decrements. So you had too many decrements to do in the pause, so you put some of them later, and so that requires doing some sweeping later as well. All right? So you can, when the lazy decrements are done, you can now sweep the mature space, but you're finished with the nursery. So however much memory you got back from the nursery, you're always getting some back in the collector. Sorry, I forgot to mention, it's also a generational collector, so you're always collecting the nursery as you go. And then we've talked about the right barrier already. And then if you aren't getting enough memory back, you trigger a trace to reclaim the cycles. And that, you can see the orange on the bottom, that says, ooh, I don't think I have good enough. And this is a real trace taken from the middle of a GC on one of the programs that we were tuning the system on. So this aren't made up numbers, actually. Justin.
Yes, I wanted to know how low level you described
Before you do the write, you store the source pointer in a buffer if it's never been written before, okay? And why do you do that? Because you're doing reference count, all right? So if this object was mutated, and it's pointing to something, you store the target, all right? So on the first mutation of an object, you want to reference count the target, so you need to know that this object changed and the subject of the write changed, but you don't need to know every single write. So you can coalesce the writes to this object between each GC. So you only need to record the source object one time. All right, and that's an optimization that Res Pertrank invented in like a decade ago for reference count. And so that means that you don't have to reference count the nursery, actually, because you can just trace from the roots and reference count the nursery as you see those objects are live for the first time. And since most writes are in the nursery, that's a really important optimization for reference count.
The other question I go with is it possible to design heaps that are self-defracting?
So you saw the heap organizations that we've got.
Like a free list with that, follow that?
No, because you have to copy in a free list to defragment it. And compaction, you have to do an extra pass to defrag it. So the sweet spot is the hierarchy of lines and regions in IMIX, which you can reclaim some of the free memory in a block and do smaller amounts of copying to defrag. Okay? That's what you should have learned yesterday.
I was thinking about, like in certain file systems, they don't require defragmentation, and I was wondering if there was some type of parallel there with memory.
Because you have to store, like even in a file system, you could waste quite a bit of it,
Yeah.
right? Okay. All right. So now, here's the result for Lucene, which is you're doing things concurrently, and your latency is as good as G1 but no long pauses. All right? And then comparing to G1, Shenandoah, and LXR on and also ZGC, because this collector is working in OpenJDK, so we can compare against all of those. You can see significant wins over that sometimes, like on Tomcat, Shenandoah is performing the worst, but on H2 it's performing better than G1 compared to Shenandoah and G1, but LXR is dominating them all in latency on all of them. So all of these benchmarks have a special methodology because they are like we have to measure the latency of the requests, and that's what we're optimizing here is tail latency of a human interaction program. Ricardo.
Why is there a big spike on G1 and H2?
Performance problem at, we didn't debug that. But any GC can decide, oh, I need more memory or I need to do something. So if you run out of space and then you collect and you don't get any space back, you have to do an emergency GC and do the whole heap. And so I assume that looks like that to me, but we didn't debug it, so I don't know for sure. Because I've seen stuff like that before. Now, these benchmarks are just throughput benchmarks, where you're just trying to complete them as fast as possible instead of worrying about the latency of requests coming into these benchmarks. Now we just have a fixed workload, and we're measuring each of them and seeing which collector finishes the program first, running with that. And so in that case, ZGC has a bunch of problems, and so it doesn't run because it doesn't have enough memory. This is a 2 times heap, which is the minimum heap in which the collectors can run, doubled, and so that's usually enough heap space, but for many of these systems, they need even more heap space to work well, but they require a lot of memory to get their throughput down. And so they're saying that the time-space trade-off for them is they want to use a lot more memory. And so they're tuned for a lot more memory. So you see those pathologies here in this, in what is a modest-sized heap, and you should be able to run in there. They're not tuned to run in that. And then the geo mean is a little bit better on IMIX, but the best performing one, like if your Xalin is your benchmark and you care about that, you're getting a 25% win over a G1, which is the normalized collector. And it stopped the world and not having great latency for some applications that we saw in the previous.
Hi, Kathryn. How much would you expect these results, so latency and throughput, to change when you increase the size of the heap?
So if you compare, so in the paper, there's heap size sensitivity results, and you, in order for Shenandoah to beat LXR, it needs a 10 times bigger heap, okay? And so it's just not doing any GC work at that point, right? All right. So now I'm going to go backwards in time again to when I started my career in garbage collection in 2000, really in 1999. So in 1990, first, before I do that, I'm going to talk to you about the evolution of the JVM collectors in OpenJDK, all right? So the G1 collector that we've been talking about was in 2004, and it's tracing, region-based, evacuation only, stop the work. And then these other collectors have concurrent evacuation, and we saw how that works out. All right, but in this part of the talk, I want to talk about the software engineering of those systems. So G1 is 53K lines of code. Shenandoah is 32K lines of code. And then there's a shared part of the system that's also 38 lines of code that's on top of the 53 and the lines of code in G1, for example. And then X is generational ZGC, and Z is ZGC without generations, okay? And there is no sharing between those two collector implementations, okay? So these were large monolithic implementations that were challenging to change, and you can see this snapshot was taken in like a couple days ago or like a couple weeks ago, and that none of these collectors had been changed in 2 years, okay? So that says other people are working on improving them, and neither are their authors, all right? And so these have stagnated in time. All right, so there's low code reuse between all of these. There's low maintainability, or if people are either afraid to change them or not interested in changing them, or both. And then we showed some of the performance problems that they have. All right, so what happened? So a little bit of history here. So in 1999, I'm working at UMass, And Elliot has gone on vacation to where he went on Cape Cod for 2 weeks every year. And his student, who's supposed to have a different thesis talk, but Darko Stevanovic, comes in my office and says, you know that paper at PLDI last week said there was exponential decay object models, which just says that the generational hypothesis has a problem with it because the longer you wait, the more likely it is that an object has died. Okay? Which that makes sense too. All right. And he says, I just want to do a few object studies while Elliot's on vacation, which is not my thesis. And I'm like, I think that's worth doing. Let's do that. And so by the time Elliot gets back, we've invented a collector called Older First, which is trying to get both the fact that the young objects die at a high rate, but the longer you wait, the more likely it is to be dead. And we have regions. We divide the heap up into regions, not unlike generations, but slightly different. Okay, and we can't get any results because the JVM that we've been trying to build is broken. All right, but we have an interesting enough idea and some simulation results that we get a paper into UPSLA. And I'm sitting at UPSLA watching Darko give his talk, which he did a great job. And I knew he did a great job because David Unger is known as a curmudgeon, asks a very nice question and compliments the work, so that makes us all feel good. So sitting next to me, however, is Mark Wegman, and he's less impressed. And he goes, why don't you have any real numbers, Kathryn? And I'm like, because our JVM doesn't work. And he goes, why don't you use Jikes RVM, which was the IBM JVM that they had a team of expert programmers working to make a new system to prove some ideas about Java, and they were building Java for some important customers at IBM. And I said, that would be great. And Steve was a postdoc that year, 1999, and so Elliot did all the heavy lifting on IBM open sourcing that and working with the lawyers, and Steve did the heavy lifting of going to IBM and starting to work on garbage collection inside IBM while the lawyers and Elliot were working out the contract. And then that became the open source Jikes RVM project. And the first refactoring that Steve did led to 6 papers in 3 years on innovative garbage collection algorithms and write barriers and dynamic optimization. So really, some modest, what I would call modest software engineering. So then Steve said, we can do better. And Perry Chang, who was at IBM Research at the time, he said, oh, I think we could do a lot better. Let's do it together. So then the 3 of us in 2004, and so I just list these papers not because they're great papers, but because how many papers, we had 1 simulation paper in 1999, and then we were able to produce some older first garbage collector in practice by 2002 because we had a good system, all right? And we were able to build on it. It wasn't a great system, but it was a good system. So from 99 to 2002, we got we added some innovation also to get better performance on the older first collector, all right? So then, in 2004, Perry, Steve, and I, like working mostly in 2003, published 2 papers. And one of them is the software engineering of high-performance garbage collection with good software engineering reusability, like reusing the same tracing code in every collector, reusing and I'll show you the phases of a collector and talk a little bit about what was able to be reused in a minute. And these are 2 of the highest cited papers in memory management because people learned a lot from these toolkits. And then the other thing we were able to do is Myths and Realities, the Performance Impact of Garbage Collection. And so this got a Test of Time award and from Sigmetrics. And in this paper, we really teased apart the space-time trade-offs of the 3 heap organizations. And this work led directly to the IMIX heap organization by doing that deep performance analysis. And all enabled by good software engineering, all right? So now, from 2017 to 2025, Steve, not me, like in 2016, he said, what happens if I maybe did this implementation instead of in Java and Rust? Then I could do it in Rust, and then I could make it part of OpenJDK as well as other JVM implementations. And just last week, that turned out to be a great investment, and both C Ruby and Julia are now using this MMTK toolkit that's language agnostic. Not all of it. You have to have these special. There's the paper on how you make it language agnostic and what parts of the code you have to specialize for each different language context are interesting, and Steve has a paper on that as well. All right? And so this reworking of MMTK was also enabled proving a bunch of GC components correct, and GC has to be correct or your program blows up. And so both getting the implementation performant and correct with more modular design is super, super important, okay? And so now I'm going to talk a little bit about how work packets helped us do that software engineering at the next level of modularity and resources. So it's adding another new type of abstraction at the very lowest layer of the GC that lets us build more collectors, more modularly, reuse more components, exploit parallels and better, and prove more things correct in the GC runtime. And so this is the paper I mentioned yesterday that's still not accepted, but accepting revisions at OOPSLA. So hopefully it will be accepted. So I'm going to go just a little bit through the basics on GC phases. So you have to stop the mutators. How do you stop the mutators? You have to have something that's polling that it's time to stop the mutators. And so typically the top of every loop and the top of every method says, do I need to stop for some reason? And so that's a fast test that's usually a great